A couple days ago, I accidentally gave a bad question to my calculus class. But when I realized this question was broken, it turned out to be really instructive to get into the details of how the question is broken and how we can fix it. So here's the bad question. We want to take the derivative of the inverse sine of x squared plus 1. And this was a natural question to ask at this point in my class. We just learned how to take the derivative of inverse trig functions this week. And last week we learned the chain rule, so now we're just looking at a function composition with an inverse trig function and using the chain rule to get the derivative. So at this point you might want to pause the video and just try to figure out for yourself what's wrong with this question. So I didn't figure it out until after I naively took the derivative here and then realized the answer didn't make sense. So here we go, just naively taking the derivative. We have an inverse sine function. Remember, the derivative of that is 1 over the square root of 1 minus x squared. So when I turn it into a function composition, I have to use the chain rule. And that starts out with a 1 over square root of 1 minus the argument of this inverse sine function all squared. So I have a 1 minus x squared plus 1 all squared inside that square root. And then the chain rule says we have to tack on the derivative of that argument, which is a factor of 2x. And as soon as I got that answer, I looked inside that square root and I was like, wait a minute, isn't the number inside the square root basically always negative? If we put in any value of x besides 0, I'm going to get a number bigger than 1 in these parentheses. When I square that, I get a number bigger than 1. Then I have 1 minus a number bigger than 1. In other words, a negative inside the square root. And then if we look at what happens when we plug in x equals 0, that gives me 1 minus 1 in that square root, which is fine, but it's in the denominator, so I have division by 0. In other words, there's not a single real number in the domain of this function. So at this point, I realized there had to be something I missed in the original problem. Let's go back and look at that original function and see what's wrong with it. And remember, when I write this inverse sine function, maybe you're used to writing it as arcsin, but I usually write it as sine with a little superscript of -1. This says the angle whose sine is. So we could read this as the angle whose sine is x squared plus 1. But there's a pretty limited domain of values where the inverse sine makes sense. The biggest value that I can put in those parentheses is actually 1. So we can read this as the angle whose sine is 1, and that's pi over 2. Just visualizing the unit circle there. And the smallest value that we could plug in is I could say the angle whose sine is -1, and that's negative pi over 2. In other words, the entire range of possible values for the output of the sine function is -1 to 1. So the domain of the inverse sine function is -1 to 1. So what I had my class do, just to illustrate, is just get out their calculators and plug this in. The angle whose sine is 2. Well, it's impossible for an angle to have a sine of 2. We know the sine function maxes out at 1. So their calculators all gave an error, and I had them actually try to approach 1 with this as well. The angle whose sine is 1.1, also an error. 1.01, also an error, and so on. We're outside of the domain of the inverse sine function. So knowing that the domain of the inverse sine function is -1 to 1, there's only one real value of x in the domain of this function. If I plug in 0 for x, I'm going to get the angle whose sine is 1, which is pi over 2. But any other real x value I plug in there, when I square it, I get a positive number, and when I add that to 1, I'm outside the domain of the inverse sine function. So I have exactly one real number in the domain, and it doesn't make any sense to try to define a derivative with a function like that, because a derivative is a limit of the slopes of the secant lines between 2 points on the curve, but there's only 1 point even defined on the curve. So this problem is clearly broken, but we learned a powerful lesson about how important it is to check in with the domain of the functions that we're working with in calculus. And of course, I didn't just stop there. I decided to fix the question. Now, all I had to do to fix it, so the question was at least reasonable, was to change the plus sign to a minus sign. And having learned my lesson about the importance of checking in with the domain of functions that I plan to differentiate, I wanted to find the domain of this function first. Now what we need is for the argument of this inverse sine function to be some number between -1 and 1. That's the entire range of possible outputs of the sine function. So those are the only inputs that make sense to the inverse sine function. So what I need is for the argument to be bigger than -1, possibly equal to -1, but less than +1 and possibly equal to +1. And just adding 1 to this compound inequality, What I need is for x squared to be bigger than 0. Well, we already know it's bigger than 0, but also less than 2. And now I'm trying to figure out all the x values that when I square them, give me a number less than 2. And remember, there are some negative x values that are going to satisfy this. Like -1, for example. If I square it, I get a number less than 2. So the maximum allowable magnitude of x is the square root of 2. When I square that, I get exactly 2. But again, I have to look in both directions here. I can have a minimum value of x of -√2 and a maximum value of +√2. So if I sub in either of those extreme values, I get x squared equals 2. And all the numbers in between, when I square them, I get a positive number, and it's going to be less than 2. So now that we have a reasonable domain on our function, we can go ahead and use the chain rule and find the derivative. And again, the inverse sine function differentiates to 1 over the square root of 1 minus the argument squared. So at x squared minus 1 squared down there, then multiplied by the derivative of the argument, which is going to be a 2x. So now it's interesting to look at the domain of this derivative function. We're already implicitly restricting ourselves to this interval, -√2 to +√2, but we also need to insist that our denominator is not equal to 0. So we can go looking for the values of x for which the denominator is equal to 0 by writing 1 minus the quantity x squared minus 1 all squared is equal to 0 and trying to solve for x. So I end up with an x squared minus 1 all squared is equal to 1. There are two possibilities here. X squared minus 1 could be equal to +1 or -1. Either way, we satisfy the equation. And just picking the plus sign for our first part of the solution, I end up with x squared equals 2, which means x is plus or minus square root of 2. So those have to be thrown out of the domain. And then we have the minus sign version of the solution. So x squared minus 1 equals -1. When I add 1 to both sides of that, I get x squared equals 0. So x equals 0 has to be thrown out of the domain as well. So the domain of our derivative function actually turns out to be really interesting. It's going to be -√2 to 0, where again, we're excluding those endpoints together with, so union 0 to +√2. So compared to the original domain of the function up here, the domain of our derivative function is slightly restricted. We had to remove the endpoints and we had to remove x equals 0. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.